Hi, I'm Patrick from 7bitwonders, and today we're looking at the problem haircut from the USACO 2020 US Open contest in the Gold Division. Today's topics are point update range queries, DSA, and inversion counting. As for the problem statement, long story short, we are given an array A of size n, representing the lengths of Farmer John's hair strands in order. Because he wants his hair to be monotonically increasing in length, he's defined the badness of his hair as the number of inversions of array A. Remember, we call the number of inversions of array A the total amount of pairs of indices I and j such that I is less than j, but A of I is strictly greater than A of j. To spice up the problem, a new constraint has been added. For all lengths j in the range 0 and -1, Farmer John wants to know the badness of his hair if all hair strands of lengths greater than j are set to j. So, without any further ado, let's get to the drawing board. At a first glance, it's clear we're going to have to calculate the number of inversions one way or another. And there are many ways to do that. Basically, any data structure that allows point update range queries suffices. To generalize the solution, we will need the following methods of a data structure that supports point update range queries, which we will use. The first one is query left-right, which queries the range left-right in the target array. For our particular case, we will need a sum query. The next function is add position new value, which adds a new value to the element at the desired position in the target array. Now let's recap how to calculate the inversions of a given permutation P of size n. First, we instantiate n to a valid data structure that supports those operations. In our case, we use a segment tree of n elements which have been initialized to 0. We set inversion count to 0, and for all permutations elements p of I, we check how many elements greater than p of I we have already seen. Remembering what an inversion means, we are directly simulating the process. In short, how many values we find is the amount of inversion element p of I has. In our case, if x, which we've set to p of I, is something we can actually query, the inversion count will be how many ones or how many elements we've seen in the frequency array in the interval x plus 1 and n. After querying, we must update the fact we've seen the element. The fact I chose add as opposed to a simple update or replace is because in other versions of the problem, elements may not be distinct one by one. In other words, one element could be seen one or more times, which will be the case in our problem. Finally, we return the inversion count. To see we actually understood the process, let's take this permutation P. T is the segment tree we've used in the pseudocode. Let's start at index 1. The element at index 1 is 3, so we'll have to look how many ones are in the interval or 4. We see that we don't have any ones, so 3 has 0 inversions. We also mark the fact we've seen 3 by adding 1. Now we're at position 2. We'll have to look how many ones are in the range 2, 4, which is only 1. So 1 has 1 inversion, and we mark the fact we've seen 1. Now we're at index 3, which is 2. So we'll have to look at the interval 3, 4 and see how many ones there are. So only 1, meaning that 2 has 1 inversion. And we'll mark that we've seen it. And 4, since it's the upper bound of our permutation, it cannot have any inversions. So we can, by default, say 0. So in total, this permutation has 2 inversions. Nevertheless, the problem steps up the difficulty, and rather than asking us only for the inversions of array A, it asks a different question. For all j in the interval 0 and minus 1, how many inversions will be left if all the elements of A greater than j get decreased to size j? Let's try to understand better what cutting a hair strand to length j means to the inversions of larger hairs. Let j of k be a state of j at some point in the process. If j of k is less than or equal to a of I, then a of I will be cut and set to j of k. And all the inversions that are ending in a of I will be lost, as there will not be an element greater than a of I coming before it. If j of k is greater than a of I, then a of I remains unchanged, and the inversions are preserved. Let's understand this by looking at the sample input from the problem. This is array A. Now, let's cut all the hairs which are greater than 3, meaning that A will look like this. The only hair which actually gets modified will be 5. So it will look like this: 3, 2, 3, 3, 0. If we look at the original array, we see that by doing this, we lose 2 inversions, those being 5, 3 and 5, 3. We lose them because in our case, them being equal, they do not validate the inversion property, meaning that what we've said here is true. So, the problem reduces to traversing the interval of possible values of j, now from n-1 to 0, and when an element gets cut, we remove its inversions from the global tally. Because we do it like this, we need to keep an additional array which takes the value from n-1 to 0 and output them in the other order. So we are consistent with how the problem wants us to give the answer. In the end, our final time complexity will be big O of n log n. This comes from the fact we need to calculate the inversions. Space-wise, we'll have a complexity of O of n, coming from the data structure used to query and find the inversions. And that's it. Without any further ado, we can simply go to the implementation details. Before we begin, today's video is not about implementing these data structures. So if you're curious about how I implemented this point update segment 3, you can check out my GitHub repo in the description below. So to start, we read our n and we create this segment 3 with the sum query operation. Remember, anything that handles point update range queries would do just as fine. So a Fenwick tree or a square root decomposition array would be just as valid as this one. Perhaps with worse time complexities, but that wouldn't really matter. Next up, we initialize the global inversion count and also the inversion count of each element, which we will use in the last step. So as we read our axis, we calculate how many inversions it has, we add them to the global count and also to the inversion count that element has in particular. Last, but definitely not least, we mark the fact we've seen an x by adding 1 to its frequency count. We're finally at the last step, finding the answer. We want to use an additional vector like this because we go from n minus 1 to 0, but the problem wants us to output from 0 to n minus 1, so we want to be consistent. As we remember, from the global count, we're going to remove how many inversions a cut at j removes. It may be 0 or it may be something, but because we've initialized it to 0 like this, we don't have to worry about any weird edge cases, so we can simply subtract without fearing anything. And the answer at position j is going to be how many inversions we are left with. And finally, we output our answer. And that's it. Let's see how many points we get. So let's submit it. And as we can see, it's just a streak of green. So this was it for today's video. Thank you for watching. Don't forget to comment your suggestions in the comment section below. Like, subscribe, and I'll definitely see you in the next one. Bye!